Good day. My name is Chris Henry. I'm an associate professor and water management engineer with the University of Arkansas, located at the Rice Research and Extension Center in Stuttgart, Arkansas. Here today with Gary Sitzer from Wiener, Arkansas, a rice farmer of 46 years, who just recently, we recently installed one of our pitless or variable flow tailwater recovery systems on one of his fields. And he's going to share with you his first year of experience with that. And with that, I'll hand it over to Gary.
All right, thanks, Chris. Well, we'll try to take a few minutes here and appreciate everybody from tuning in to watch and try to bring in a new ideas and a new system, kind of give you experience on it and how it all operated through the year, and we'll see how that maybe can help you on your farm. So I'll give you some idea where we're located. We're at Wiener, Arkansas, which is just a few miles from Jonesboro. It's just about an hour and a half from Memphis, about 20 minutes south of Jonesboro there. So it's Poinsett County. It's old rice area. Been growing rice for over 100 years. And of course, we're depleting our underground water and looking to do everything we can to conserve water and to use surface water where we can. This particular field is located just off Lake Hogue Road, just adjacent to the Rice and Foods mill that's located just south of Wiener. So that'll give you some idea where that area is. You can see lots and lots of rice fields in this area. One of the things we're interested in, of course, is saving water. This is an older photograph from years ago where it was fairly easy to get a lot of water just comes out of, we would cascade flood just straight out of an open riser. Of course, we do very little of that anymore. Pretty much everything's either side inlet or mirror irrigation in rice or row irrigation in soybeans. Still a fair amount of flood irrigated soybeans, but we just don't have the water volume that we used to have. So even running more pumps into a pipeline system, we can rarely get this kind of volumes anymore. So this particular field, sorry about that. This particular field, as you can see, there's Riceland. The field on the left that's got the blue marks on it is the field that we did the research in. The pump, variable frequency, tailwater recovery, system is what the initials stand for. That pump can pump up to 1,100 gallons a minute. I've seen it do that. The rows run right to left on this screen, which is east to west. The field, you can see the slope of the field. It was leveled a few years ago diagonally across there, so you can almost see the old levees out there. So we bedded it on 30-inch rows. Something new to us. It's our first year to do any row rice at all, although we've been thinking about it for quite a while. And we built an outside levee, you'll see here in a minute, that would funnel the water from the end of the rows back to that pump. The white lines, the poly pipe, we've got high pressure pipe coming from the pump up to the actual irrigation, just standard poly pipe line there. The well kind of in the middle of the field there is a diesel well that pumps about 1,000 gallons a minute. The field on the other side follows the opposite direction, back toward the east. It was in soybeans this year. Something also new for this year, you can see the thick green line up there. We constructed a new tailwater recovery pit and tied 2 wells together. So there's actually 3 different pumps in the pipeline that we used on this field. So all that was new this year. And so we were learning the new pipeline system and as well as everything else. The research fields up there in your upper left, we've got the underground pipe system in blue there. The riser is where the water went into the field. That's the northeast corner of the field. The rows on that end of the field are about 900 feet long. They're about 1,300 feet long on the opposite end of the field. So it's not a square field. The pipeline runs on back to the right to another well. By coincidence, they just worked out that both those wells pump pretty close to the same amount. You can see the tailwater ditch there. And if you're wondering why that rice looks so funky there, on the side. We had when we installed that new pump, we took an old fuel tank up there and filled it up with fuel, and came back the next day, and there was a little seepy leak in one of the seams of the fuel tank, and it kind of messed the rice up a little bit right there. This is the construction of the tailwater pit that we did this year, and here it is as it's starting to fill up there. So it's not a huge tailwater system, but it definitely helps, and helps us conserve the water. We'll catch some of the water from our own farm in that area. We've only been there for since 17 on this particular 2 farms, and some of the neighbors' tailwater will also come back into there. And that being a pit deal, once it gets full, it runs off. So it also functions as drainage too. So that's the way that one's designed. This is the opposite. That was the opposite end of the field there, where the water is overflowing, and this is looking toward the east. This is looking back toward the west, and it's completely full and overflowing into that vertical pipe there. The thing standing up there's actually a handle. It has a very heavy back flap valve on it, and later, when it's empty and you may have water running in from both directions back into it. That's a heavy back flap valve. So we designed a handle system to kind of chain that up, make the water flow easier, so it doesn't have to push to open that big heavy valve in there on that. So if you can see the diesel pump up there in the corner. It's one of my neighbor's fields that we don't farm off there. That's got some fallow ground down at the bottom of the field, and if he lost some water out of his rice field, it would flow back into this one. Just give you some idea about the rest of the farm. We rent a farm that's about 4 or 5 miles north of here, and this research field. The big water basin there in the bottom of the picture is an 80-acre reservoir that was constructed over 20 years ago. There's about 750 acres of plantable ground in this farm. It's 100% surface water farm. Virtually every drop of water that falls on that farm can be recirculated, can be brought back by ditches back to this reservoir. And stored. It also has access to bio-to-view for surface water. This also is rented out by the landlords for duck hunting in the fall. And if you see the other blue stars out across there, the first one is the second reservoir this landlord constructed after the 2012 really dry year, because we were down to rationing water. It was getting really short, and so they constructed the second reservoir, and it's all integrated, tied together with underground pipe, and basically can move water around just about everywhere. And the farthest star is one of my friend's farms. He constructed a 35-acre reservoir just a few years ago, and behind those trees, this will be the first year he's actually constructed a second one there, as well as some on his other farms. So this part of the world is going to surface water as fast as it can afford to. It's a very expensive proposition, of course, to do that. At some places you just don't have much choice. One of the things we want to, sorry about this thing being a little touchy on flipping. What we really want to talk about today, though, is the surface recirculating pump here, the variable frequency pump, or what I call a sump pump. You can see there's not a great stand that rise here early in the year, and that's part of the problem we'll talk about a little bit later that we got into. But that is a variable frequency, so it can speed and slow down. It's got a 5 horsepower, 220 single phase motor on it, so it needs very little power, very little energy consumption there. So it turned out, I was really, really skeptical about it, whether it'd have a fit or not, but it turned out to be something pretty much proved the concept. So I was pretty happy to be able to participate in it. We actually started talking about this in the year before, and this is we actually installed the sump area there, which is basically kind of like a corrugated grain bin type stuff. About halfway up, it's got perforations in it, kind of like a grain bin floor to let the water come in. The bottom's solid, got a solid bottom in it. As you can see, it's fairly compact, but all you really need is a backhoe to install it. You can carry it all on a 16 to 18 foot trailer and pretty much get it all installed in one afternoon. So it's a fairly simple concept. As far as just installing from the farmer's end. You can see the variable frequency control panel there and some of the plumbing and stuff that go with it. And so it wasn't really too terribly complicated to get it put in and installed there. So we also used plastic flashboard drainage control structure there. Right beside of it. So we wanted along the highway for easy access, and it just happened to work out for this field. And it's quite a conversation starter for the neighbors as it was took a couple of years to get it up and running as to what the heck Crazy Gary was doing out there. So but that always fun when you got something right along the highway that you're experimenting with. But after we got it installed, you can see this is about the time we first putting the first watering on the rice. That's the flashboard again. We got a little bit of leakage there. We had to work on that a little bit. I think those plastic boards got warped just a little bit when it was transported, and we, other than that little bit of leakage up there, we really didn't have hardly any water leave the field all year. We put short pieces of pipe underneath there to, we wanted a way for the water to get out so that it could get to the overflow and it wouldn't move the pipe around, either the poly pipe or the rigid pipe. So that's what we did there. And that worked pretty good. You can see it's kind of a grassy area around there. That was just kind of by accident, but actually ended up helping us over time because it kind of helped filter the bean stalks and this and that might have floated up in there early on before we got the water deeper. We did use diamond high pressure pipe. That's what you see there to go uphill. And we pushed it uphill roughly 5/10 before it went into the poly pipe that was actually doing the irrigation. The standard poly pipe, and the poly pipe itself was not level. It actually went uphill. So we had a couple of feet of movement there, probably total on that. So there's later in the season, you could see the rice coming along, and we actually, that field had dumps on two sides of the field, but doesn't have one there, at least not yet. And so we just used the regular rice levee plow, built a levee along the end to control the water, and it used the levee furrow there to help funnel the water off the end of the rows down to the pump itself. So it's a blue dotted line there, shows how the water flowed back to the pump from the ends of the rows, and that all worked out pretty well. Pretty simple setup there. Later in the year, when we talk about yields here in a minute, you can see there's a little unevenness out there, and it's actually a lot worse than it looks in this picture. The field was leveled fairly recently, and for some reason, the cut fill areas, some of them are actually toward the bottom of the field, and it didn't, and us not knowing what we're doing with bedding, we actually borrowed a roller bedder from a neighbor because he had one handy, and we really didn't, we maybe went too deep, and anyway, for whatever reason, we had stand issues down at the bottom, and it kind of hurt us all year long and ended up hurting the yield in that area of the field. Here's a closer look at how that's set up. You can see the telemetry antenna. So, it's hooked up to, a flow meter, and then it actually, long term, we might be able to work out, the researchers might be, where, if you had an electric well or electric pump putting the water into the field, they could communicate together and speed each other up and down, and you could get really sophisticated with it maybe over time and get the bugs out of it. But we didn't have any of that going on this year, just trying to get proof of concept, make sure it worked. But if you see the 2-inch pipe on top that turns around, comes down, that's actually what can be used or is used as a pressure relief system. So if you got too much pressure backing up there, it flows out, that flows right back into the pit. So that also worked pretty well, because Crazy Gary messed up a couple times and maybe didn't push the buttons just right and had a little more pressure than we should have had, but didn't blow anything up, and it worked fine. Just another angle of it there. You can see the flow meter there. It's also hooked up to telemetry, and worked out good. Just a vertical 5 horsepower motor. It's fairly simple. Of course, everything's economics. We'll see what the cost of something like this would be if we go into more mass use of it, and how many of those we'll be able to afford to put. It'd probably be pretty expensive on just like a 47-acre field like this, but worked out pretty decent, and learned a whole lot. There's that picture there in the pump itself that could show the overflow actually running at that time. And the wiring there's the sensor. It's got a float valve in it, so it's reading how much water it's got, and it's speeding the pump up and down. And like I said, I've seen it pump 1,100 gallons a minute, and it'll slow down, just almost nothing, and even start and stop. If need be, if you want to run it that way. You can see the perforations in there to let the water in, and to filter it so it doesn't get a bunch of trash in it and stop anything up. So all that surprisingly worked, really better than I thought. I was pretty skeptical about a bunch of it. Thought that we'd end up with a lot more problems, but didn't really happen. So worked out to be a better deal than we thought on as far as just ease of use, and getting in there. Here's the inlet part of the field. It looks kind of convoluted, but we didn't get all the material together at the very start. We didn't get that flow meter installed until after the 4th of July by a few days, and we kind of curved it around there, trying to get water into the very edge rows up against that dump, which were, like I said, a new construction of underground pipe, and nothing was leveled up exactly the way we wanted it. So you can see the little blue gate 2-inch open close on there at the pipeline, where we're actually letting some water out there to try to work it around and get in those edge rows. And it ended up getting it in there and working out pretty good. So didn't really have any dry rows that we couldn't get any water on at all. Although it looks a little crazy, we did have some beds that just never looked like they were totally wet. And of course we were afraid, particularly my crop scout, you'd have the big nemesis there with the pig weeds or any other weeds. I mean, every week he was basically, he was just certain we were going to grow over the next week. And, it never happened, either because we were doing a better job watering it than we really thought, or because we got enough rainfall, whatever. Of course, the trick, and this field does not have a tremendous pigweed pressure on it. So I realize a lot of people have got a lot worse problem than I do. So, and I'm certainly not an expert on row rice production, but we did overlap a lot of residuals. It was a clear field. So we had a couple of shots of New Path, had a couple of shots of Command. We had Prowl in there, and basically ended up with a really clean field. We probably didn't have but 2 or 3 pigweeds out in the field. There may be in a handful right along the very edge or something, as border effect, where you end up with pigweeds around the edge, no matter what you do a lot of times. But we had some of that. This is the moisture sensor system. We did get one of those also put in there a little bit later in the year, right after the 4th of July, I think. And that's what sits down in the ground. We did it for monitoring purposes. I didn't really get into trying to use it extensively or at all, really, to time the watering. We kind of timed it by the weather forecast, and both me and the crop scouts kind of opinion on where we were on the rice itself, and all of that. So here's the unit as it's solar powered, how, it's got the telemetry on it. So Chris could monitor it from wherever he was, and it worked. It's a good tool. We need to start using them more probably. Here's the data off of that. You can see we never field capacity was 26. I don't think we ever got down to even 35. So, although it looked drier than that, particularly to the crop scout, he was about to come unglued every time he could see something that wasn't muddy. But as it turned out, we kept it pretty wet, and didn't have any issues there with as far as moisture management. That worked pretty good too. Here's the water, going into the field. So we had to move it away from the dump a little bit because there was a dump there, and all the issue. We used blue, 2-inch open close gates, try to water the rice off to the other side of the poly pipe there. So we didn't have a whole lot of burned up rice. Didn't really have any anywhere in the field there. So as far as that goes, so that worked out pretty good. So what we learned, what were the results? This was a Rice Tech XL 745 clear field. Pretty much everybody in our part of the world thinks, if you're going to do row rice, you do a clear field prep, and you do a hybrid because it just gives you more options, and the hybrid's so much tougher on taking any variances that might come along. Most of this area is either Henry or a Hillman silt loam, fairly flat. We planned it May 4th, got it up May 19th, which was a little long. That's kind of an average date because the problems we talked about earlier in the bottom. So we went on and started getting stuff set up there between the 8th and the 22nd. The 8th was actually when we started getting ready to put fertilizer on it, I think, rather than emergence. After we got the flow meter on, it measured 8.2 inches. So we kind of estimated what we did before. I think the maximum would have been somewhere in that 17-inch area, which is, not the best, but certainly a pretty good savings involved. We ended up with 161 dry. We had a lot of variance in moisture. Everything was kind of opposite what I expected. We weren't expecting that cut fill area to give us problems. That, didn't come up good. It was thin. It came up, it was later. That end of the field was 21.9. The high end of the field was 16.9 when we cut it. The last time it was in 2 years ago, it made 199, even though it had been leveled. So this year it was off some, although our whole farm was off a little bit too. The field right next to it, next to that tailwater ditch, that was conventionally flood irrigated and didn't have any dirt cut fill issues really. It made 193 under mirror irrigation. So we did take something of a yield hit, but the vast majority of it was due to that emergence issue in the cut fill area. Basically didn't lose any water off the field hardly at all. As far as that went. So what did we learn? Basically, we think that going forward, this field waters easily, in levees or any other method. So we're probably, would get the bigger bang for a buck. If we moved it some of our steeper fields. We did try one of those. It wasn't in this research project this year. And, it had a yield reduction also, but it worked out fairly decent. And we got a lot more savings from not building the levees and worrying about rice going down between them and all that. We're going to have to learn, depending on what kind of bedding system we end up on, if we go much forward on this. First out of the box, I really didn't know what we're doing. We drilled it at an angle. Might have been the wrong angle. Might not have been the right thing to do right then. We probably need a shallower bed, just basically water for us. But with borrowed equipment, we didn't want to mess his equipment up by doing a bunch of changing the way he had it set. It certainly changes your water management, and you're thinking. There's lots of times we actually went 10 days without putting any other water in the field because we were able to get recirculating water in it. And even though this wasn't a typical field where the poly pipe was completely flat, we learned how to kind of manage that, and gave you a lot of flexibility so you could maybe not hold that flood at the bottom as much. If you thought a rain event was coming, you could go ahead and pump that down and catch that. And we did that some. So all in all, it worked out, pretty good. And I think still got a lot to learn, but it's certainly an innovative system, and we'll see what cost and risk rewards work out in the future. And I want to really thank Chris for putting this together and helping me get it where I could present it. And I'll turn it back over to him.
All right, thanks, Gary.
And that was way over 20 minutes, wasn't it?
My name is Chris Henry. I'm an associate professor and water management engineer with the University of Arkansas Division of Agriculture. This is a follow-up presentation to Gary Sitzer's discussion of the novel tailwater system he put on his farm. Thank you for being a guinea pig, Gary. So we're going to talk about this novel system, the original research system, and we have tried to do is develop that even further in 2020 and try some new things. So that's why I've titled this presentation, How to Grow 200 Bushel Row Rice Without Any Solid Urea and Only a Foot of Water. I have a lot of support for the work that I do, namely the USDA NRCS, which really funds the installation of the commercialized product that you saw earlier in Gary's presentation. But my program is also supported by the Arkansas Rice Checkoff and the Rice Research and Promotion Board, by Rice Tech, and by the many chemical companies that help me out in managing our weed pressure. So thank them for their part as well. So with that, I'll list my objectives. These are really the questions that I tried to answer in 2020. Can we use no-till fertigated rice continuously? If we can stay in this, kind of keep the beds maintained, can we make this work? It has a lot of savings involved with doing this. Does fertigated rice use more water than flooded rice? It's been a question that has vexed us for years. There's this perception that fertigated rice uses more water than flooded rice systems. So I think we've answered that. I'll show that later on here. Is there a yield penalty for fertigated rice? What can we do to not have to shovel furrows as much in fertigated rice? We made an attempt at that question. Is environmentally safe nitrogen a viable fertilizer for fertigated rice? I'll show you why I think that's got some potential. And then this year we really focused on trying to fertigate row rice. We've done this in the past. We've shown that it works, gives us the same, no significant difference in yield when we use urea. So this year we tried to actually apply it to the whole field and implement it. And then we spent a lot of time on managing irrigation. How do we decide how far we can go in fertigated rice without any yield penalty? So those are questions we tried to answer in 2020. In our first 3 years, we worked a lot on the farm with doing paired comparisons with farmers. And so from 2016 to 2018, for 3 years, these are the results we found, and I've talked about these before. We found that row rice actually used significantly less water than Miri rice in the first 3 years, saving about 12%, but no yield difference, but it was approaching significance. We also looked at net returns in this subset, and Dr. Ranjit Main with UAPB looked at the net returns and found no difference in net returns between row rice and Miri. Now we extended this study, now it's 5 years. We collected some additional data and we pulled this all together. And the results changed a little bit. What we found is there's no significant difference in water use now. Although furrow rice uses numerically less water than flooded rice, it is no longer significant. It's kind of right at the edge of that, or had been around the edge. In yield, we actually now found that it was kind of marginal, but now it's strongly significant that there is a yield difference between fertigated rice and Miri rice. And then that yield drag is around 13.7 bushels per acre. So I want to thank the county agents that helped collect all this data. It's a very large data set of 28 paired fields on farmers' fields across the state. And we've really been able to kind of nail this down. So I think we busted the myth that row rice is a big consumer of water. It's really not any different than a multiple inlet irrigated rice field. Actually, probably uses a little less water, could use a little less water in certain years than a Mary field. So we've asked you before, and farmers have reported to us, does row rice use any more or less water? And generally people think these are the same or a little less, which reflects our results that we found in our study. How much of a yield reduction is acceptable for fertigated rice? And everybody's reporting anywhere from a 6 to 15 bushel. Most of you reported 6 to 15 bushel is acceptable. And we're right at 13, so that's right in the range of what most people think might be acceptable for a yield drag in row rice and still be accepted. So motivations for growing row rice, what many people often tell us the reason we do it is there's less labor and less tillage. Those are the two biggest reasons for looking at a furrow irrigated rice production system. So our study field is 40 acres. Each plot is half an acre. It's the full length of the field. We irrigate using this novel pitless variable flow tailwater recovery system, same system that you saw in Gary's presentation. It's been patented. Gary's one of the first to help commercialize this. Before we would irrigate every 3 to 5 days using sensors and watermarks, but now we use this variable flow system, and it's so much more flexible. So you can just add water just like you would a flooded rice field when you have it, and it just continues to recirculate it. So it makes the management of the water so much easier when you're trying to manage rice fields. We put basic normal fertilizer plan to start out with, 60 pounds of phosphorus, 60 pounds of potassium. We added some sulfur and zinc, applied this right before we planted. And then we used tissue samples during the season to actually manage or decide how much nitrogen and micronutrients to put out through the irrigation system. And we used 32% urea ammonium nitrate instead of urea. So all through the irrigation water. So no nitrogen except through the irrigation water. We used Rice Tech full page 7521. All the beds are no-till. They've been no-till for 4 years since 2017. It's been continuous rice since 2016. So we fight barnyard grass just like many of us do. We're resistant. Our barnyard grass population, we know, is resistant to new path, propanil, and grass. And so we applied gramoxone. I've got the whole pesticide, herbicide, and pesticide program there that we used in the program. As always get asked that. So the pitless system, basically what it does is we put water into the top or the crown pipe and goes down the furrows. There's a shallow area at the bottom. We kind of dam it up less than 100 feet, and tailwater pump picks it back up, pumps it back to the top of the field, and we just continue to recirculate water around it. So as the bottom gets low, we just add water, usually twice a week, pump it back up, and then we just continue to recirculate water the whole season. Makes it fairly simple. You can also just add a little bit of water, whatever your ET is, constantly, and it will just maintain a constant depth, which also works. We've done both. This is kind of what it looks like in the field. Very low cost, very low pressure, very low energy. So how we manage the rest of the field, basically we try to burn the rice off in the fall or the spring. Usually we don't get it done until spring, and so we still have some residue out there. We apply fertilizer, ground application. We use this Perkins furrow runner. Preferably, I really like to do this right before we plant, right in front of the drill. Then we drill and plant, spray a pre-emergent down, and then we irrigate right away to activate the chemical unless it rains. And that's how we've been managing it for several years. So when to irrigate fertigated rice. Key difference between fertigated rice and other crops is, I think, the effective rooting depth that we have to use to determine the water balance. So do rice plants exhibit, so that's the first thing we've been trying to nail down. Then do rice plants exhibit yield limiting stress earlier than other aerobic crops? And that's really been the question we haven't known. But through several years of study, I think we've started to answer that question, have much better recommendations for that. And then how do we measure this water balance effectively so that we know how far we can go? And so we put some tools together that should help with that. Most farmers tell us that they irrigate every 3 days or every 4 to 5 days. That's pretty common. Almost nobody goes 7 days. and nobody reported doing 10 days. So that's how we crafted our study originally. In 2019, we do fully irrigated, which is every day, with a continuous system every 3 days, then every 7 days, and every 10 days, and we found no significant difference in yield, although numerically there is a yield difference. In 2020, we find nearly exactly the same result, and no difference in head rice yield. Again, no significant difference in yield, except there's a numeric difference, and 3 days being the highest yield. So what we find when we look at the soil moisture data is a 0 day. So the blue line is field capacity. So anything above that line is saturation. The red line is the wilting point. So both the 0 and 3 day, we're holding above, well into the saturated zone. So above field capacity. So it's pretty wet. The ground's mushy. You can step on it, makes a hole, because we know we've tested the field capacity in this soil is around 36%. That's the blue line. The wilting point is 8.9%. At that point, the plants are dead. So this 7 and 10 day is a different picture. And these essentially become about the same treatment. But in the later part of the reproductive phase, we get to really high deficits or really low, really dry conditions because we're a long ways now from field capacity. We're getting a lot closer to wilting point. And so we should be experiencing stress. We only put an inch of water on, so we only do it every 10 days. So we're not meeting crop water demand. So we know at these levels that these plants should be stressed. We're trying to create stress with this 10-day irrigation sequence. And so we can get a yield drag if there is one. And so we do accomplish this in 2020 pretty well with the 7-day getting one extra irrigation in there. But for the most part, because the rain and the length of period, they match up pretty well as basically one treatment, even though they're two. So again, no significant difference in yield, although numerically there's a difference. If we irrigate every day, it's going to take about almost 35 inches of water, 34.9 inches of water to irrigate to keep up with that level of water in the field. Using a variable flow system, we only use 12 inches, just over a foot of water. If we go to a 3-day irrigation cycle, we drop our water use from 34 to 23 inches. If we go to 7 days, 16, 10 days, 14.9 inches. Even at 10 days, we can't do as well as a variable flow system that puts on 12 acre inches. The volumetric water content just before irrigation is above field capacity every time for basically the 0 day and 3 day, and gets around 25% for the 7 and 10 day, the average. The range is a little bit wider as we go out further days. Gets a little closer to the wilting point, but still reasonable ranges. And 14 and 18 is actually pretty dry condition. When you walk out in the plots, the ground's pretty hard and dry. So going back and looking at what's the allowable depletion just before we irrigate, on average is 11 to 41%, or it's always above field capacity 0. 3 day barely gets past field capacity. 7 days, 41%, and 10 day is 38%. If we look at the highest allowable depletion that we hit just before irrigation, we're looking at 41% is the absolute driest it gets at one point on 3 day. On 7 and 10 day, it's almost 80% and 65%. We know we assume stress in most crops accumulates after 50% allowable depletion, so we should have had some stress in that 7 and 10 day. And is that reflected in the yield at 7 and 10 day? But again, no significant difference statistically, but numerically we think there could have been some stress accumulate there. So that's what we found with the relationship between the water and the yield in this study. Looking at total water use efficiency, the variable flow system where we recirculate has the highest water use efficiency in this subplot. 7 day follows, then 10 and 3 day. You see there's some differences in this significance. No difference between 7 and 10, they line up pretty close. And then every 3 day and every day are not different from each other from a water use efficiency standpoint. But big difference in the total. So we've done some similar work with subsurface drip irrigated rice using parental lines and different allowable depletions. And we found essentially the same answer in that study, that this 40% is kind of a magic number for allowable depletions. After that, there may be some stress fall off. So we aggregate all that data, we kind of found the same thing. Watermarks. So this kind of brings me to watermarks. How would you use watermarks to manage irrigation in irrigated rice? So my standard recommendation has been 4, 6, or 8, 12, and 18, which is different from our other row crops. Use an effective root zone between 12 and 18 inches, depending on those last two sensors. And looking at the data now, what we've been seeing, something in the 30 to 40% allowable depletion range would probably be acceptable to use with our mobile app. Watch the slope at the end. When you terminate, basically you can watch and see the plants as they stop using water. You can see that on the sensor trends, and that look at the rice, you can pretty well determine when it's time to pull the plug and drain the field for a harvest. And as always, you can always use visual observations along with the sensor data to make sure the sensors are representing the field and not seeing stress out there. So, but I think with this information and our app, you have some better information, better tools to manage some irrigated rice if you're using watermarks. Okay, the next topic I want to talk about is environmentally safe nitrogen, or smart nitrogen. ESN is a controlled release nitrogen fertilizer consisting of high quality urea within a unique polymer coating. And the coating forms a protective barrier that acts as a semi-permeable membrane. So what happens is this urea is coated, and as it gets wet and breaks down, the urea is released through the polymer and slowly releases nitrogen in solution. It just basically slowly dissolves over a period of time. And so this has been used in the Midwest in corn for a long time. We wanted to see if we could do it in row rice. So why ESN on rice? This is what it looks like. This is how hairy my field was, right when we planted it. So we planted and sprayed right after we put the ESN on first, so we incorporate it. We had found in the past, the last couple of years, that we'd used the race half ESN and half urea, basically at the 4 to 5 leaf stage, and we haven't found any yield benefit, and we hadn't found any yield drag either. University of Missouri has recently published some data suggesting a yield benefit for percentage of the total nitrogen coming from ESN. And so we wanted to see if we could apply ESN at pre-plant. At the same time, we apply our P and K because, wow, this would be nice to be able to put all of our fertilizer out at once and then go plant. Run a fur runner through, put a fertilizer on, then go plant. Let the planter basically work the fertilizer in. That would save a lot of time managing nitrogen later in the season. Critical, one less thing to manage. So this also, by doing this, kind of takes away any issues with ESN floating away. It is lighter than water and can float, but once you plant behind it, it works it in, and you almost can't find it anymore in the field. So what we did was ESN all up front at pre-plant. Then we put urea on, the same amount of urea on at 3 to 4 leaf. Urea, then we dropped the rate to 125, put a little extra, trying to use the ESN on the top end only because it's a little bit more expensive product, to see if we could bring the top end yield up. Then we did the same thing with urea, try to get the same across all 4 stages, the same amount of nitrogen. And so what we found was there's no significant difference in yield. They all came up with the same result. So we're not seeing a benefit from the ESN. It's not causing any yield drag, even though numerically it's a little bit lower. That difference isn't significant, just a couple bushels. So that's what we found with ESN. I think there's some potential for it. I wanted to show you this picture. This is a picture of the ESN plots right next to the urea plots, right about the time we fertilized the plots. And what's kind of interesting is when you put the ESN down at pre-plant, there's nitrogen there available for the plants when they come up. And so they come up and stay greener, and they fill out a little quicker. And so 2 things that come to my mind is you don't usually want to put nitrogen out because your weeds will grow. But if we've got good pre-emergent herbicides, we can take advantage of that, let the rice get up and grow a little faster before we have to use our post-emergent herbicides. So real interesting questions about ESN and weed control yet to be answered, but that was an observation we noticed this year. Tillage. Do you no-till or do you till? We found the first year that we had a yield drag when we tilled, and it was significantly different. But the last 2 years, we've not seen a significant difference in yield, although numerically the conventional tillage is a little higher, but it's not very significant. So I think there's any, don't think there's any advantage to tilling. One of the big issues with fertigated rice is shoveling out furrows. And so this year we tried to lay some plastic mulch down to see if we could use that to keep the beds from eroding. This stuff comes in 500-foot rolls. It's not very expensive. But we had too much water get out past and erode it, and so it didn't work. But I think we used 36-inch mulch. I think next year we're going to try 60-inch biodegradable mulch because it's kind of hard to pick it back up. On the biodegradable, you can leave. So we're going to try that and see if that works next year. But we had a lot of shoveling, as anybody who has tried fertigated rice can attest to. So my crew is not real fond of this part, so we're trying. But didn't really work, but we'll try again. We used some different polypipe products this year that just came out. We used the Delta Plastics Revolution pipe, which is a half-mile roll. On our study, we also used the Delta Plastics Delta Diamond, which is a high-pressure pipe in our study. And we also used the Dancer Connections polypatch, which I really like because it's really easy to make repairs. When you have a little pinholes or animal damage in your pipe, you can just cut this stuff and peel it back and put it right on the pipe. So that was help when we had small breaks. This is what it looked like when we rolled out the pipe and put the mulch out and the pipe. This is kind of what it looks like. When we did it, we used GPS and our polypipe printer to print the hole sizes on the pipe as we rolled it out. And then after we roll it out, we went ahead and started to fertigate. Or this later in the season, I guess, when we fertigated. So this is the first time, to my knowledge, anybody's tried to fertigate a large area. We basically use a small generator, a small fertigation pump, specialized pump for this purpose. We fertigated 32% UAN right into the polypipe through chemigation valve. We did it 3 times with 50 pounds of nitrogen per acre each time. And then we had a boot application for part of the field. Total in was 170. We'd irrigate for 10 hours, and 3 hours after we started, we'd fertigate for 7 hours. And once the water got to the end, we would shut off, let everything soak in. We'd wait a day or however long, maybe a day or so, and then we'd fire back up, usually the next day or the day following, and continuously irrigate the field then for the rest of the week. And we also sampled the tissue and used Green Seeker to see if we were short of nitrogen anywhere in the field that we could find. Another picture of what it looks like. This is a chemigation valve, so it has a backflow preventer, has an injector, a low pressure drain, air vacuum relief, and a flow meter. And this is to prevent any fertilized contaminated water to come back into your well or into your irrigation system that you don't want, which we do, so no nitrogen gets into anybody else's study accidentally. This is our tissue analysis that we looked at kind of through the year. So if we ran DD50, it's calling for the last date for nitrogen at 610. We sampled, saw we had plenty of nitrogen in the tissue, so we waited, get our system all put together and working. I've got the minimum deficiency values, which are kind of a range. We stay above the minimum deficiency the entire season, except in the very end. We wait 2 weeks after the latest date by DD50 to actually put any fertilizer on the field. And that holds us pretty good until we see a drop about the end of June. And then we go ahead and put 2 more and put the rest of about 100 pounds on those 2 times, 2 events, a fairly short period of time around the 4th of July. Put the rest of the nitrogen on the field. And we save the last 20 pounds till the very end, till the boot. We saw it goes down. So we set up a boot application trial then at the end of the study to see if that was going to make any difference. And I've got green ring here, so you kind of see roughly where in the boot, you kind of see where in the season we were with the tissue analysis. Okay, so we don't really see in our study anymore, we don't see this mohawking effect that often happens. We don't see height difference between the furrows and the beds. We don't see very much difference in the grain moisture from top to bottom now because of how we irrigate and because of the no-till. The yield difference from the top to bottom has decreased over the years. We don't see as much yield difference. It's actually pretty small than it was in earlier years. And so the boot end, this is the result of our boot nitrogen study, which is another sub-study in this field. So we saved some of it. We did put the extra 20 pounds on. And so with that, most of the field averaged the 207. And then the 150 without the boot was 210. That was our highest yield. No significant difference in yield. No significant difference in head rice yield. We did see a difference actually in the plant tissue analysis. It's approaching significance. So there was a difference in plant tissue, but it doesn't translate to yield in this particular study. We used extensive green seeker data. My guys were out there walking all over the place, looking for deficiency in the field. We flew it, looking for deficiency in the fields. We couldn't find anything. We end up with about 8.1 bushels per inch to give you some perspective of the water use efficiency. The only person that has done better than that is the irrigation contest winner this year. He got 8.7 bushels per inch, beat me by a little bit. But the contest average was 4.6. So 8 is an extremely high water use efficiency. So this system was very efficient with water. So the take-home messages, we saw about a 14 bushel per acre yield drag. So expect that on average with fertigated rice. Not going to happen every year. I think we've busted the myth. You're not going to use more water than Miri if you use fertigated rice. Probably actually a little less, not significant, but it looks numerically. Pre-plant ESN shows some real potential. I'm really interested to do more with ESN because I think it could really help reduce some of the labor and you can focus on other things such as weed management and irrigation. Large-scale fertigation was very successful, kind of a neat tool for making up nitrogen shortages later in the season, or just putting all of your nitrogen out that way. I think what I've learned is that fertigated rice is more resilient than we think. You can do lots of different things and it seems to really come out okay. We don't see a huge difference in yield across all of the studies and the plots. For irrigation, I suggest using that 12 to 18 inch effective rooting depth. 30 to 40% allowable depletions seem to be reasonable for decision making. We ran much higher depletions and did not result in significant yield penalties. So this kind of 3 to 5 day frequency that most people are doing seems to work pretty well. Keeps us near this field capacity range. I'm probably going to stay around that field capacity. So, but I'm not going to be afraid of doing a weekly irrigation on row rice because it's not going to, especially if you're putting a full irrigation out and keeping it at 40%, I don't think it's going to show up any yield penalty. So that's all I have. Thanks for listening, and I hope you enjoyed the session. And here is the QR code for your CEUs. Enjoy the rest of your day.